In Module 3, Section 4, we will discuss an introduction to problem solving. Now this is just a refresher. You may have seen this chart, or you should have seen this chart in Module 2. But these are some phrases that you will use when translating a word problem to a mathematical expression or a mathematical statement. In no way is this an exhaustive list, meaning there are other words that could represent addition, subtraction, multiplication, and so on. But this should get you started. When you see something that's synonymous to more than or increased by, hopefully you will recognize that as addition, and so on. You may want to print this page or copy this chart or find a page number reference in your book from your instructor, because these keywords are very important as you go through the problem solving process. In general, this is the strategy for problem solving. First, you want to understand the problem. And that can only happen if you carefully read the problem, reread the problem. And once you understand what's going on, you will choose a variable to represent the unknown. A lot of times that will just be x, but you can choose whatever variable you want unless the instructions state that you must choose a specific variable. In some instances, it's helpful to construct a drawing, and then you would propose a solution. You may think of a solution without writing an equation. You may actually create an equation. But at this point, you're really just trying to wrap your head around what's being asked, what's the unknown, what does the unknown stand for, and so on. Step 2, you want to translate the problem into an equation. Step 3, once you have an equation, you need to solve the equation. And step 4, use the common sense test. Does your answer make sense? If you're talking about the cost of a vehicle, is it something reasonable in the thousands and not in the billions? Make sure that your answer matches the criteria that are set forth in the problem. Let's try an example. Now, no two word problems will be exactly the same. That's why we have a general process. So don't be frustrated or irritated as you come up to problems that don't exactly fit the mold of every example. Try to apply the general problem-solving technique. That being said, let's try the first example. The product of twice a number and 3 is the same as the difference of 5 times the number and 3/4. Find the number. Okay, so here we're not told that the number has to be a specific quantity or a specific variable. And so what I'm going to say is x equals a number, or the number that we're looking for. So anytime we see a number or the number, I'm going to underline all those situations. There we see a number. Again, we see the number. At the end, we want to find the number. Every time we see that phrase underlined in blue, that represents x. I'm now going to go through and circle all of the keywords that can be translated into mathematical operations. So the product is a mathematical operation term. Twice, the same as, difference, 5 times. We also have a few other pieces of important information. We have 3 that will be used, and 3/4. So let's put all of this together and see if we can write an equation. So we have the product. Product means multiply. A lot of times the operation will be listed first, and then the 2 factors or the 2 terms will be listed second. So product means multiplication. I write my multiplication sign. Now let's figure out what's being multiplied. The product of twice a number. Now remember, a number here is x. Twice a number would be 2x. So 2x times, because we want the product of twice a number and 3. 2x times 3 is the same as. Is the same as means equal. So 2x times 3 equals the difference. Again, the operation is given first. The terms will be given second. Difference means subtract. So I write my subtraction sign. The difference of 5 times the number, remember the number is x, 5 times x, and 3/4. So the difference, that told us we would have a subtraction expression. And then we were told what would be subtracted. 5 times the number, 5x, and 3/4. Now we have an equation very similar to what we would have seen in the last section. Let's go through the same process we would have before and find the solution. So we start by simplifying each side. On the right-hand side, we don't have any like terms. On the left-hand side, we have a multiplication problem. 2x times 3 is 6x. So we simplify a little bit. 6x equals 5x minus 3/4. At this point, I'm not going to get rid of the fraction, and you'll see why in just a moment. I'm going to go ahead and just draw my vertical bar through the equal sign to separate both sides of the equation. Let's move all the variables to the left. So we subtract 5x. When we do that, the opposite 5x's cancel on the right side. That leaves us negative 3/4. On the left side, 6x minus 5x is just x. And we already have a solution. X equals negative 3/4. So the number that we're trying to find, x, is negative 3/4. Let's try another example. The sum of 13/5 and 3 times a number is equal to 32/5 subtracted from 4 times the number. Find the number. Again, the unknown number in this case is not given a variable that it must be represented by. We could call it x. Let's just call it something different for example's sake. We'll say n equals the number. It really doesn't matter what variable you choose. So if n equals the number, let's go through again and underline every instance of that phrase. A number. 4 times the number. Find the number. So n will be the value that we are trying to find. Again, let's go through the problem and find any operational keywords. Sum, difference, times, anything like that. So we start with the sum. 3 times is equal to subtracted from 4 times. We have a few other additional pieces of information that will be useful and necessary. We have 13/5. We have 32/5. And you can see on these types of problems, there's not a lot of fluff. It's very straightforward, and almost every word or number is necessary. So let's go through and see if we can take the blue circled words, the red underlined phrases, the boxed values in green, and form an equation. So we start with the sum. The sum means addition. And just like on the last example, it tells us the operation first and the terms or factors second. So the sum of 13/5, so one of our terms is 13/5, and 3 times a number. Remember, this number, in this case, we just said it was going to be n. 3 times a number would be 3n. So the sum, we are adding 13/5 and 3n. We are then told it is equal to, write our equal sign, 32/5 subtracted from. We haven't seen this phrase in a while, but remember, anytime we see subtracted from, we should think reverse. You must flip. Very important. So subtracted from, it tells us the operation is subtraction, but the first number mentioned will go behind the minus sign. The second number or variable mentioned will go in front of or to the left of the minus sign. So 32/5 subtracted from. So write the 32/5 last, subtracted from 4 times the number, 4 times n or 4n. Now we have our equation. Again, we could go through without getting rid of the fraction. In this example, let's go ahead and eliminate the fraction so we can get a good refresher of how that works. We have one denominator throughout the entire problem, and that denominator is 5. So let's multiply all 4 pieces by 5. We're going to multiply both pieces on the left side both pieces on the right side. I'll go ahead and draw these arrows. It tells me I need to distribute that 5 to every term. You may want to pause the video. I'm not going to show this step broken down like we have in some sections. You multiply every term by 5, and this is what you will get. 13 plus 15n equals 20n minus 32. The fractions are gone. We draw the vertical bar through the equal sign. Let's move all of our variables to the left side, all of our numbers to the right side, and continue to solve. So we subtract 20n from both sides. And when we do so, the opposite 20n's cancel. We're left with 13 minus 5n equals negative 32. Draw the vertical bar through the equal sign again. Let's subtract 13 from both sides. The opposite 13's cancel. Let's come up to the top. On the left-hand side, we're left with negative 5n equals negative 32 minus 13 is negative 45. We are multiplying negative 5 and n. To cancel, we will divide by negative 5. The negative 5's cancel on the left side and give us n equals negative 45 divided by negative 5 is positive 9. Let's try another example. Now here we are told we want to use x as the unknown number. So we're not trying to get fancy with the unknown. We're told it needs to be x. Using x as the unknown number, write the statement below as an equation. Now here, it's important to note that we are not told to solve the equation. We just want to set up the equation. 4 times a number minus 9 is equal to 3 times the number plus 2. So again, in this case, we're told that x is the number. Let's go through the same way we have before and underline that phrase. The number. We will now go through and circle any of those mathematical operator terms. 4 times minus is equal to 3 times plus. Those are all keywords we're going to use in translating. And then we have some necessary pieces, the 9 and the 2. Again, this isn't a problem full of fluff or unnecessary information. As you can see, every word is underlined, circled, or boxed. So now let's go through and see if we can translate. We start with 4 times a number. Remember, this number is x, so 4 times x, or just 4x, minus 9, so minus 9, is equal to 3 times the number. Remember, that number is x, so 3 times x, or 3x, plus 2. Now, because we were just told to write the statement, that's as far as we need to go. Had the directions said we need to simplify, we would continue to go through the process of solving this equation for x. Let's try a word problem where there will be some unnecessary information. So this won't be a direct translation like we've seen in the previous examples. A car rental agency advertised renting a car for $28.95 per day and 32 cents per mile. If Greg rents this car for 4 days, how many whole miles can he drive on a $150 budget? So let's go through, and just like we had before, let's determine what the unknown quantity is. Let's determine the necessary information and then try to set up an equation. If we go to the very last sentence, we are asked how many whole miles. That is the unknown quantity. So I'm going to say x equals miles. So anytime we see mile used in this problem, let's underline it just like we have in the past. And let's use the blue this time instead of the red. So how many whole miles? We know that's the unknown value we're solving. If we go back through the problem, we see 32 cents per mile. That will also represent the unknown value of x. Now let's look at any mathematical terms. That will help us in the translating. This is one we haven't used yet, but per. I underlined it here. We really needed to circle it. Per. Per is going to represent multiplication. I know budget here doesn't seem like a keyword. It's not one you will find on the list that was shown at the beginning of this section. We'll talk about why that's necessary, a necessary operator, in just a moment. Let's also go through, we're going to use the red this time to box. Let's box any other important information. $28.95, that's going to be useful. 32 cents, that will be useful. 4 or 4 days, that's necessary. $150. Now, as we look at this word problem versus some of the problems we've seen previously, there's a lot more fluff in this problem. So we have to be a lot more discerning of what's useful and what is not useful when we get to some of these real-world types of word problems. Let's see what we can do now as far as setting up the problem. Let's start with the fact that we have a $150 budget. Well, if we have a $150 budget, my costs at the most can equal $150. So let's write that. Costs equal 150. We're willing to spend all of our money on the car rental, or at least all the money that we budgeted. On the left-hand side, let's try to determine what the costs actually are. As we go through the problem, we see that renting a car costs $28.95 per day. So that we can start there. $28.95 per day. Now remember I said per is going to represent multiplication in this particular problem. So $28.95 times the number of days. As we continue to read through the problem, we see that Greg rents the car for 4 days. So we start with $28.95 times 4. Now, if there are any other additional costs, we will add those to the car rental cost or the daily car rental cost. So we put a plus sign. We continue to go back through the problem, and we see that it will also cost 32 cents per mile. So 32 cents. Again, per means multiply. We want to multiply by the number of miles. If you remember, we decided that the miles were actually the unknown value we're trying to find. So here we're going to multiply by x, 32 cents times x. And we can continue to read through the problem and see those are the only costs that Greg will have to worry about as he rents this car. So $28.95 for 4 days plus 32 cents for every mile, you don't know how many miles, should equal, at the very most, his $150 budget. Now we have an equation that can be solved. We start by multiplying $28.95 times the 4 days that he rented the car, and that gives us 115.8 plus 32 cents times x is just 0.32x. That equals 150. Now we've seen problems in the past where we have decimals and we've multiplied or moved the decimal place in order to get rid of the decimals. I'm not going to do that here. If you choose to do that or you feel like it's necessary for you to solve this problem, that's fine, and you should get the same answer. So let's draw the vertical bar through the equal sign and isolate x. So we start by subtracting 115.8 from both sides of the equation. We do that so that the opposite 115.8 will cancel. So on the left-hand side, we're left with 0.32x, and that equals 34.2. Now, because we are multiplying x by 0.32, we need to divide at this point. So we divide by 0.32 on both sides. Those cancel on the left-hand side. Let's go up a little higher. That gives us x equals, now as we put this value in the calculator, 34.2 divided by 0.32 equals 106.875. That is the absolute maximum number of miles we can drive. Let's use our common sense test. Let's use our brains to go back through the problem and see what needs to be done. If we look at the last piece underlined in blue, it says how many whole miles. Well, if I have a decimal, that's definitely not a whole mile. So we need to eliminate the decimal. And typically we would round this number up to 107. That would give us a problem, a big problem. We only have enough money for 106.875 miles. We don't have enough money for 107. So for this particular example, we're going to round down to the next lowest whole mile. And Greg will have a little bit of money left. He doesn't have enough money for 107 miles. He'll have a little bit of money left if he only drives 106. So we have a whole mile answer. We haven't gone over budget. And X is the number of miles Greg can drive in those 4 days with the information given. Okay, let's try a different example, and you'll see many problems like this in your homework where we're talking about integers, whether it be consecutive integers, even integers, odd integers, and hopefully you remember what integers are. Those are those numbers that we count with, as well as 0, as well as their opposites. So 1, 2, 3, 4, 0, -1, -2, -3, -4, and so on, both directions forever. Now the first thing we need to find are the next integers. It tells us that we start with an even integer. It doesn't tell us what even integer we started with. It could be 2, it could be 4, it could be -100. It's some number that is an even integer, and it wants us to find the next 2 even integers. So to do that, let's make a chart and try to follow the pattern. Let's say we start with 2. Well, if we start with 2, we know the next even integer would be 4. The next even integer would be 6, and so on. We could also write that a different way. If we started with 2, 4 is 2 plus 2, and 6 is 2 plus 4. Let's try to make this pattern work for a different set of even numbers. What if we started with 8? The next even number would be 10, or we could say 8 plus 2, couldn't we? After 10 would be 12. We could write that as 8 plus 4. And we could continue this pattern forever. Instead, let's put an x in place of our 2 and in place of our 8. To get from x to the next even integer, we would add 2 more. And that's true all the time. If you have an even number and you add 2, it gives you the next even number. Well, if we get to the next even number, we would add 2 more, and 2 plus 2 is 4, so x plus 4. So in this example, if my first even integer is x, then my next even integer will be x plus 2. This is always true for even integers. The third even integer would be x plus 4. And now we filled in our table. Let's look at the last cell in our table. It says the sum of the second and third even consecutive integers. Well, if we look, x was the first, x plus 2 was the second, x plus 4 was the third. So if we want the sum of the second and the third, we add x plus 2, because sum means addition, remember, x plus 2 plus x plus 4, and now we can combine like terms. I have x and x. I have 2 and 2. X plus x makes 2x. 2 plus 4 gives me 6. I can't combine like terms any further than that, and that's the solution. Let's try another example. Here we want to fill in the blanks with not consecutive even, but consecutive integers. Consecutive integers would be 1, 2, 3, or 10, 11, 12, counting by 1 or adding 1 each time to get to the next number. And so if we made a chart and tried to find a pattern just like we did in the last example, if we started at 2, then the next number would be 3, the next number would be 4, and 5, and so on. Well, another way to write that, 3 is the same thing as 2 plus 1, 4 is 2 plus 2, 5 is 2 plus 3. We can continue that pattern using the first number to represent every following number. What if we started with 11? Well, the next number would be 12, or 11 plus 1. And then 13, or 11 plus 2. And then 14, or 11 plus 3. And we could continue this pattern with whatever number we chose to be the first integer. But instead of having an actual number, we're just wanting to put x in its place so that we can start anywhere at any given time. Following the same pattern we used with 2 and with 11, we're going to use x and add 1, and then use x and add 2, and then use x and add 3. And we'll continue to add 1 each time to get to the next consecutive integer. So as we fill in the blank, if our first consecutive integer is x, the next consecutive integer is x plus 1, and then x plus 2, and then x plus 3. We've now filled in for the first 4 consecutive integers, starting with x. So we go to the last cell in our table, and we determine what we're being asked to find. The sum, remember sum is addition, of the first, second, and fourth consecutive integers. Let's mark those. The first is x, the second is x plus 1, the fourth is x plus 3. So we add those three numbers together, x plus 1 plus x plus 3. So now we want to combine like terms. We have x and x and x. Those will combine to make 3x. We have 1 and 3. Those will combine to make 4. No more like terms, so we're finished combining and simplifying. Let's try one more example using types of consecutive integers, just so that we can see all three. We saw consecutive even, we saw just consecutive integers, and now we have consecutive odd integers. We're getting that information in that last cell in the table. Consecutive odd integers, similar to consecutive even, 3, 5, 7, or maybe 39, 41, 43. Odd numbers are numbers that end in 3, 5, 7, or 9, as well as 1. Those are odd integers. Even integers are those that end in 2, 4, 6, 8, or 0. So let's try with odd integers to find a pattern. Let's say our first odd integer was 5. Then the next would be 7. Next would be 9. Well, let's rewrite the 7 and 9 using the first integer. 7 could be 5 plus 2. 9 could be 5 plus 4. Well, what if we started with 9? The next consecutive odd number would be 11. That would be 9 plus 2. Next would be 13, or 9 plus 4. And now let's see if we can find or use this pattern that we've just found, where we add 2 and add 4. If we wanted to go farther, we would add 6. And instead of starting with a number that we know, start with a variable. Start with an unknown odd integer. Let's start with x. Following the same pattern, the next odd integer would be x plus 2. The next odd integer would be x plus 4. Now, don't let the fact that we're adding even numbers confuse you. If you start with an odd number, you always add an even number to get another odd number. And so it should make perfect sense that if we start with an odd number and we add 2, we have the next odd number. And if we add 2 more, or if we add 4 to the original, we have the next odd number, and so on. And so filling in our blanks, if we start with x, the next odd integer is x plus 2. The next odd integer is x plus 4. So really we have the same type of pattern with even integers and odd integers. We go to the last cell in our table to determine what we're actually trying to find. We want the sum of all 3 consecutive integers. So we have x, x plus 2, and x plus 4. All 3 of those need to show up in the simplified sum. So x plus 2 plus x plus 4. We find our like terms. We have x and x and x. That adds up to 3x. We have 2 and 4, and that adds up to 6. 3x and 6 are not like terms, so that's it. That's as far as we can go. 3x plus 6 is the simplified sum. Let's try one application of using consecutive integers. And that will be this word problem. To make an international phone call, you need the code A for the country you are calling. The codes for country A, country B, and C are 3 consecutive integers whose sum is 93. Find the code for each country. So first we are told the answers for A, B, and C are 3 consecutive integers. We can go back to one of the previous examples to see how we can find 3 consecutive integers. That would be represented with x, x plus 1, and x plus 2. Those would be 3 consecutive integers. Let's go through the problem and see what other pieces of information are useful. We see the word sum. We see the word is. Those are mathematical operations. We also have 93. That's an important and necessary piece of information. So we have 3 consecutive integers whose sum is 93. Let's see what that looks like. So we take all 3 consecutive integers, and sum means addition. So we add them together. Whenever we see the word is, that means equals. So the sum is, or the sum equals 93. On the left-hand side, we combine like terms. So we combine the x's, we combine the numbers, and that gives us 3x plus 3 equals 93. On my vertical bar through my equal sign. We subtract 3 from both sides. In order to isolate x, the opposite 3's cancel. And this becomes 3x equals 90. We can now divide both sides by 3. And x equals 30. So the first consecutive integer is 30. Now remember, consecutive integers we're counting by 1 each time. So the first country code is 30. The next number then would be 31. The next number would be 32. 30, 31, and 32, in no particular order, are the 3 consecutive integers that represent the country codes for country A, country B, and country C. Remember, not all of the word problems will be exactly like the examples you've seen, but follow the same process. Look for the important words, the mathematical operative words in the problem, and ignore the fluff. Work hard and do the best you can.